Okay, this video is going to be about examples for lesson 4, where we talked about OR cases specifically and disjoint events, which is the special case for that. This first problem says in a group of 20 children, 3 have red hair, 8 have blonde hair, 5 have black hair, and the rest have brown hair. If a child is chosen at random, what's the probability that the child will have brown hair? So pause the video, give this one a try, and then unpause and see if you're correct. Okay, so maybe when I was doing this, I would probably list out the possibilities, right? We have red hair, we have blonde hair, we have black hair, brown hair. That's everything. And we were told that 3 children have red, 8 have blonde, 4 have black, and the rest have brown, but it was a group of 20 children total. So I think I could just add these up and subtract from 20 to get that there are 5 children left, and they must all have brown hair. We're going to need to have that because we are going to ask a question about the probability of brown hair. So one way to solve this problem would be it's equally likely that we have any of the children chosen. So this is a simple probability, and that means out of the 20 children, we just need to include all of them that have brown hair. If it's equally likely, it's just the number of children with brown hair divided by the total number of children, which would be 5 out of 20, and therefore 0.25, right? Now, there's another way you could solve it if you want. You could say the probability that someone has brown hair is 1 minus equals 1 minus the probability of the complement that we have any hair that's not brown, right? And so that would be 1 minus this, right? Now, the reason I put this in the or case is that you can have not brown hair by being red-haired, blonde-haired, or black-haired, right? So that would be the probability that you have red, or, right? So it could be red, or the probability of blonde, or the probability of black hair, right? So really, this could be 1 minus, and then it could be the probability of red, which is 3 out of 20, and then the probability of blonde is 8 out of 20, and the probability of black is 4 out of 20, and for OR, we know that we typically add the probabilities. These are disjoint cases. You can't have red hair and blonde hair at the same time, one or the other, so you would just add with nothing to subtract there, and then that would turn out also to be, it's 1 minus 15 out of 20, which turns out to be 5 out of 20, which is that same 0.25. That wouldn't be a shorter amount of work, but it also would be correct. Okay, let's look at another problem here. If we draw a single card from a standard deck of 52 cards, what's the probability that it's a 7 or a face card? So pause, try the problem. Okay, so to write this out, the probability that we have a 7 or, that means we should use the union symbol, 7 or, I'll use FC for face card, then the OR formula says that we would have the probability of it being a 7 plus, we add the probability of being a face card, but we have to subtract any probability of being a 7 and a face card at the same time, right? So what are face cards? Face cards are anything with human faces, jacks, queens, and kings, right? So since there are 4 suits, hearts and diamonds are red, clubs and spades are black, there's going to be 4 jacks, 4 queens, and 4 kings. That means a total of 12 face cards out of the 52 card deck, right? All right. And some of those are black and some are red, but none of those are 7s, right? So if I draw a single card, is it possible for it to be a 7 and also a face card? No, that's not possible. That's not possible because all the face cards are jacks, queens, or kings. So this probability here of being a 7 and a face card, that's 0. It's impossible. So all we have to do is add up the probability of being a 7, which there are 4 7s in the deck out of 52, with the probability of being a face card, which there are 12 face cards out of 52. So that would turn out to be 16 out of the 52 cards, which turns out to be 0.3077, so a little over 30% chance of getting a 7 or a face card. Now, whenever we use the OR formula, many times, not always, but many times we could also use a Venn diagram. It would also be appropriate to do the problem this way. Let's have a circle of 7s, and then we'll draw a circle of face cards, but like we said, it can't be a 7 and a face card at the same time, so that would be a separate circle, right? And how many cards are in here? Well, we have 4 sevens, we have 4 face cards, and then we have a total of 52 cards in the deck. So 7 and face card means you would add up all the ways in the union, right? The 4 plus the 4, or sorry, not 4. There are 12 face cards. Let me back up. There are 12 face cards in the deck, right? So you would add up 4 plus 12 out of the total of 52 cards, and that would also get you to 16 out of 52, or 0.3077. So if you prefer, you can kind of be more visual and do it with a Venn diagram, recognizing that 7 and face card don't overlap, or you could use the OR formula and the intersection is 0. The and probability is 0. Okay, the next question here says a community college has 1,000 freshmen, 800 sophomores, 700 juniors, and 500 seniors. If a student is selected at random from the college, what's the probability that the student is a junior or a senior? A junior or a senior. So pause, try the problem. All right, so the individual probabilities here, one way to do this would be to say the probability of being a junior is, well, let's see, we have a total of 1,000 and 800 and 700 and 500. That's a total of 3,000 students in the, so if I randomly choose, then they're all equally likely to be chosen. Then there are 700 juniors out of 3,000. So the probability of a junior being chosen would be that fraction. And the probability of a senior being chosen would be the 500 seniors out of 3,000, right? So the probability of a junior and a senior being chosen, right? Wait, sorry, or, I keep using the wrong formula here, or a senior union, right? Using the formula would be the probability of junior plus the probability of senior, but we have to subtract off the probability that a student is a junior and a senior at the same time. But is it possible for a student to be a junior and a senior at the same time? No, that's not impossible. That's not possible because you're either a junior or a senior. Those are disjoint or mutually exclusive cases. So then we would just add these probabilities. 700 out of 3,000 plus 500 out of 3,000 turns out to be 1,200 out of 3,000, which is 0.4. So there's a 40% chance that in this college, if you choose a student at random, you would get an upperclassman, a junior or a senior. Okay, let's take a look at this one. It says in a survey of U.S. households about cell phone ownership, the following data was obtained. 6% of houses has 0 cell phones, 23% there's 1 cell phone in the house, 35% 2, 28% 3, and 8% 4 or more. What's the probability of having 1 or 2 cell phones, 2 or more cell phones, fewer than 2? And then are the events having 2 cell phones and having 3 cell phones disjoint? And are the events having less than 3 cell phones and having more than 1 cell phone disjoint? So pause that, try all the parts of this problem, and then unpause, and we'll talk about the solution. Okay, so as I'm looking at this, I'm thinking, let's just do it one at a time. The probability of having 1 or 2, which would be the union, right? That's the probability of having 1 plus the probability of having 2 minus the probability of 1 and 2. I'll use the other notation here. This would also be the intersection, the and symbol, right? So can a house have 1 and 2 at the same time? That's impossible, so this probability would be 0. So this probability of 1 or 2 would be the probability of 1, which is 0.3, plus the probability of 2, which is 0.35. So you would just add those up and get 0.58. So if you were thinking we just need to add the numbers for those categories, you'd be absolutely right. The categories are disjoint from each other. There's nothing to subtract as far as an overlap, and or is add, so you would just add that up, right? The probability of having 2 or more means we need to include the probability of 2 plus the probability of 3 plus the probability of 4 or more. So we would just add up those numbers, 0.35 plus 0.28 plus 0.08, and that adds up to 71% of the population there. That's the probability. And the probability of having fewer than 2 cell phones, less than 2 cell phones, well, that's just the cases on this side, right? So it would be the probability of having 0 cell phones plus the probability of 1. And so we would just add up the 0.06 plus the 0.23 to get 0.29. Okay, so the first 3 have to do with just adding up the appropriate categories. Okay, for the next part, are the events disjoint, right? So let's look at that, right? Disjoint, also known as mutually exclusive, means they don't overlap. So let's look at having two cell phones. Having two cell phones is this particular spot right there. Having three cell phones is this particular spot. Is there any overlap of that? Right? So for D, I think we would say there's no overlap. And what that means is that these are disjoint. These events are disjoint, also called mutually exclusive. There's no joint probability. There's no probability of them happening together at the same time. Right? But what about having less than three cell phones and more than one cell phone? Right? So less than three cell phones would be anything less than three. That would be this. And probability of having more than one would be 2 and 3 and 4 plus. And there is an overlap here. There is an overlap here. So there is overlap. So you would have that these events are not disjoint. Are not, sorry, are not disjoint. Because there is an overlap, right? Right? This probability, the probability of having less than three and the probability of having more than one, right? That probability is 0.35. That would be referred to as the joint probability of those two events because they happen together 35% of the time. All right, anyway, the answer to the question is they're not disjoint or not mutually exclusive. Okay, let's look at this one. It says a particular model of automobile is manufactured in 3 plants in the U.S. 50% of the cars are manufactured in Detroit, 20% in Spring Hill, and 30% in San Antonio, as given by this tree diagram. The event is a car manufactured in Detroit, and a car is manufactured in Spring Hill. Are those two things disjoint? And then if one of the model cars is selected at random, what's the probability that it was manufactured at the Detroit or Spring Hill plant? So pause this and then try it out. Okay, so the first question is, are they disjoint, right? So disjoint means that there's no overlap, right? And if you just look at the tree, right, they could be manufactured in Detroit, they could be manufactured in Spring Hill, but something's not going to take both of those paths. So whenever you have a tree diagram, the individual ends of the tree are always disjoint cases. Right, so these are disjoint. There's no overlap there. If you're at one place on the tree, then you're not also at another place on the tree. Okay, and then it says if one of the models is selected at random, what's the probability that it was manufactured at the Detroit plant or the Spring Hill plant? So we're finding the probability of Detroit or Spring Hill, which would be the probability of Detroit plus the probability of Spring Hill minus any overlap. Detroit and Spring Hill, but we just said that those are disjoint, so this probability would be 0. So all I have to do is add the probabilities for disjoint or for Detroit and for Spring Hill, and that means there's a 70% chance that the car came from Detroit or Spring Hill. All right. So just 3 more problems to look at here. There's not as many problems here just because there's so many times where we combine the or along with the and that'll cover it in the next couple videos later where we have a lot more possibilities. Okay, this one says a jar contains 10 balls, 4 green balls, 3 red balls, 3 purple balls. If a single ball is selected at random from the jar, what's the probability that that ball is a red ball, a purple ball, or a red or a purple ball? So pause this and give it a try. Okay, so let's see. For the probability of red, right, that's just going to be all the balls are equally likely to be drawn. We have 10 balls, and 3 of those are red, so that probability would be 3/10. Okay? For the second part, the probability that we have a purple ball, again, we're drawing 1 ball out of the 10. They're all equally likely, and there are 3 purple balls there. So that would also be 30% chance of getting a purple ball. And then for the third one, it's the probability of a red ball or a purple ball being drawn. This is the or symbol. And so that would be the probability of a red ball plus the probability of a purple ball minus the probability that a ball is red and purple at the same time, right? Now, if I draw a ball out, it can't be red and purple at the same time. So this probability here would be 0. This is a disjoint case again. So probability of red, right, would be 0.3. Probability of purple, 0.3. I subtract 0. That probability would be 60%. Okay, let's look at another problem. It says two events, C and D, occur with the following probabilities. Probability of E is 0.3, probability of F is 0.6, probability of E or F is 0.7. And we want to find out if events, that should say, these should be the same letters. So this should make this E and F, E and F. Probability of E and F mutually exclusive. Find the probability of E or F. Okay, so pause this and give it a try. Okay, so let's see. Probability of E and event mutually exclusive. That's another word for disjoint. So let's maybe look at it this way. If we have these events E or F, one of two things is true. Either they overlap, which means they would be not disjoint or not mutually exclusive. Those words mean the same thing. Mutually exclusive, right? Or it's this situation where they do not overlap, right? Which means that they would be disjoint. These events would be considered disjoint events or mutually exclusive events. Okay, so what determines that is whether there's an overlap, right? And that overlap is the probability of E and F occurring at the same time. So the question is there a probability of that or is there not a probability of that? So for us to find that out, we're going to have to figure out what the probability needs to be. What am I looking at here? Two events. Oh, I skipped a problem. No? Okay. Yeah, let's look at these two things. We're going to have to figure out this and probability here. So how can I do that? Well, I've got the or formula. I haven't even really talked yet about the and formula. That's coming in a later probability video. But I have this formula that's true in both these cases. It's that the probability of E or F is equal to the probability of, you know what? I think this problem is poorly formed. Let me change the problem slightly, and I apologize for this. I'm going to go back and erase this, and you can pause the video and start this again. There's a bunch of typos in here. So this one should say the probability of E, and this one should be F, and this is E or F. Okay, that's what I'm intending to find. Okay, and then actually this symbol here, this should be the probability of E and F, right? We were asking us to find something that was given. Okay, so let me reconsider the problem. The probability of event E is 30%. The probability of event F is point. Actually, let's see. Let's change this also. I'm going to change this also. The probability of F is going to be 0.4. Let's leave the probability of E at 0.3. So those are the three givens. Probability of E is 0.3, probability of F is 0.4, and the probability of E and F is 0.7. Is that what I want to do here? I'm sorry, confusing things here. Let me look and make sure I'm doing the right problem. Before we start this, I want to make sure the problem is doable and is going to give us a meaningful answer. I think there's typos here. So let me step back for a second here. That one, this one. Okay, so this is that problem. Okay, now I think I've got it straight. Let's redefine this whole problem. We're going to call this probability of C is 0.3. We'll say the probability of an event D is 0.4. And we'll say the probability of C and D is 0.1. Okay, good. And then we're finding out are C and D mutually exclusive, and what's the probability of C or D? Okay, good. This is a solvable problem. So now try this one. Pause this one and solve it. Okay, so let's take a look. So again, we have that same thing we talked about. Mutually exclusive means that we would have to know whether or not we've got C and D, right? This would be mutually exclusive, right? Or if they do overlap, C and D, then that means these are not mutually exclusive, right? What it depends on is whether there's a probability for C and D occurring at the same time. And actually, they told us that probability was 10%. In this case, the probability of overlap would be 0. This would be 0, right? But that's not true in this case. We do have that the probability of C and D is 10%. So that means there is an overlap. And the answer to part A is that, that these are not mutually exclusive. C and D are not mutually exclusive. And the reason for that is because the probability of C and D is not 0. So that would be probably the best way to write that if you had to explain the reasoning. And then it says to find the probability of C or D. Right? So now that I know that it's the probability of C or D and there is overlap, we could use the formula. Probability of C or D would be the probability of C plus the probability of D minus the probability of C and D, because we don't want to double count the stuff in the middle. Okay, so that probability would be, well, the probability of C they told us was 0.3. The probability of D they told us was 0.4. And the probability of the intersection is 0.1, so we would have to subtract that. So that would give me 0.7 minus 0.1 is 0.6. That would be that. Now, if you wanted to use the Venn diagram instead of the formulas, we've been kind of doing the formulas throughout here, but you could use Venn diagrams. You could say, let's fill out this Venn diagram over here. Okay, now when you fill out a Venn diagram, you always want to start with the innermost part. So the probability of C and D is 0.1. So you can use either counts or probabilities. I'm going to use probabilities. That probability in the middle is 0.1. And then it says the probability of C is 0.3. So this entire circle, C circle, has to contain 0.3. But 0.1 has already been accounted for, so there's 0.2 remaining over there. And then the probability of D is 0.4, but I've already accounted for 0.1 in the middle, so 0.3 is left. If I add all those up, 2, 3, 6, that's 0.6 total. That means there's 40% left to be outside to add up to a total of 100%, right? And the entire Venn diagram has to add up to a probability of 1.0. So that's the Venn diagram. And then what you could do is you could say, now I'm looking for the probability of C or D, right? And that's the union. So it'd be the union of all the numbers that are in the union of those two circles. So I would just add up the 0.2, the 0.1, and the 0.3, and that also gives me 0.6. So you could use a Venn diagram if you prefer to do that rather than the formula, but just make sure you fill out from the inside out so you can account for what you've already seen. Okay, one last problem in this video. Two events, E and F, occur with the following probabilities. The probability of E is 0.3, the probability of F is 0.6, the probability of, okay, I'm going to fix the typo right here. This is supposed to be E or F. Yep, E or F is 0.7. And the question we're asking is, are events E and F mutually exclusive? So give this a try. Okay, so just a reminder, right, the situation is we either have mutually exclusive, which means that E and F don't touch. There's no joint probability. They're disjoint. They're mutually exclusive. Or we have an overlap, in which case they are not mutually exclusive or not disjoint. Okay, so it comes down to, is there an overlap? What's the probability of E and F? Because if that probability is 0, then it's mutually exclusive, and if it's not 0, then it is not mutually exclusive. So I think I'm going to go back to the formula again. I think that's the best way to solve these kind of problems. The probability of E or F, and you can use a Venn diagram to remind yourself, it's going to be the probability of being in circle E plus the probability of being in circle F, but we have to subtract out the probability of being in E and F, the intersection at the same time, so it doesn't get counted twice. That's actually how I remember that formula. And so if I plug in what I'm given, the probability of point E is 0.3, the probability of point of F is 0.6, the probability of E or F would go on the left side as 0.7, then I should be able to solve for the probability of E and F. So I'd have 0.7 equals 0.9 minus probability of E and F. And so that means the probability of E and F would have to be 0.2, because I'd have to subtract 0.2 from 0.9 to get 0.7. And since that is not equal to 0, it means it's this case. There is an overlap, and that means that E and F are not mutually exclusive. Okay, so that would be the answer to that. All right, so like I said, kind of a small number of problems there, and also in the next video when we're going to focus on just the AND video. But on the following video, we'll mix AND and OR together. That's a lot more flexible, so there's a lot more examples there. Okay, thank you for watching these.